типические многоуровневые модели, чтобы посмотреть, как они делаются в R, значит, что там, какой показатель означает, какой коэффициент. Значит, далее я хочу следующий скрипт будет посвящен не самый первый, тому, как отбирать модели. Потому что есть некоторые правила, я боюсь, что не все о них знают, значит, которые надо соблюдать при отборе моделей. Значит, когда решать, что лучше, что хуже. Там есть нюансы. Значит, третий момент, который я хочу осветить, это визуализация результатов. Потому что когда вы делаете многоуровневую модель, у вас получается там 50 коэффициентов разных. Значит, это нужно уметь представить как-то на графиках. Значит, вот это я хочу тоже, ну и сами какие-то показательные случаи, как показывать, значит, контрастные какие-то случаи, чтобы понимать, что делает ваша многоуровневая модель. И, наконец, последний момент, если времени на это хватит, я хочу осветить логистическую многоуровневую регрессию. Значит, ну вот такая программа у нас на 2 дня. Значит, давайте посмотрим, как она у нас пойдет. Значит, давайте первый слайд покажем. Значит, начнем мы с очень простых вещей. Значит, смотрим и видим, что в принципе все похоже на линейную обычную модель, но значит, альфа J здесь не является константой. Интерцепт здесь не является константой, а интерцепт здесь является переменной. Причем если x у нас варьирует по I и J, где I это первый уровень, например, респондент, а J это второй уровень, например, страна. So alpha varies by J, which is, for instance, country, whereas X varies by both I and J, which is the respondent level and the country level, right? So, so this intercept is a random variable rather than a constant, as it is in classic regression, right? Press the board again, please. Yes. So, alpha here is modeled as another constant, and actually this is the only constant in the model, plus some unexplained variance on the J level, that is on the country level. That is, we say that there is intercepts vary, but we do not know why they vary. So the second level variation here is left unexplained. Can you press again? Yes, and then we can combine these two equations into one equation and we'll get the mixed equation. Therefore, these models are sometimes called mixed models. There are several names for them. Mixed models, random effect, fixed effect models, or multi-level models. These are all synonymous. So, in the mixed equation here, we see that there are two constants, gamma 0 and beta, right? And two random effects, that is the country level random effect, eta J, which adds to gamma, and therefore the intercept in each country is unique. And then there is unexplained residual variance on the individual level. After, and this is important to notice, after the country level variance has been taken into account. So epsilon stands for individual level variance within countries, because the country level variance is covered by eta J. Therefore, epsilon is individual level variance within countries. Okay, so this is the difference. If this is clear and there are no questions, we can move on to the next slide. So I will start with a very simple model now, which is called an empty model. Sometimes it is also called an ANOVA model. We'll see shortly why it is called an ANOVA model. So in this model, we have no explanatory variables at all, right? So there is no x. We only have alpha j, that is the country level variance, that is totally unexplained, and epsilon alpha j, which is the individual level variance within countries, which is also totally unexplained. Can we press again? Yes, so we model alpha j as in the previous model. So it is a constant plus unexplained variance on the country level. And the mixed equation looks as follows. There is a constant, which in this case would be, I guess, a mean, right? Grand mean, right? Then there is eta j, and when we combine gamma 0 and eta j, we get country means. And then we have epsilon j, which covers the remaining, that is, individual variance within countries. Okay? So for the empty model, people often calculate intra-class correlation coefficient, or ICC. This is how it is calculated, and it is basically alpha variance over the sum of alpha variance and epsilon variance. In other words, this is country level variance divided by the total variance, right? So therefore it shows, as is clear hopefully from this formula, that it represents the share of group variance in their overall variance of y, and thus it describes how different the groups are. At the same time, it also can you go back? Control L. You do Control L. Yeah. At the same time, it also describes how strongly units, individuals, within each country, for instance, or units in the same group, resemble each other. And therefore it is called correlation, because intra-class correlation, that is, correlation within countries, correlation within the units of the second level. So because if countries are different, very different from each other, and it takes a lot of total variance, right? Mm-hmm. Then relatively little variance remains within country.
Means that within countries responses are
very similar to each other within each country.
Mm-hmm.
They are different between countries, but they are similar within countries. And this is why this is called a correlation, because correlation generally shows how similar things are, right? Okay, now we can move on to the next slide, unless there are questions.
Okay, I have a small question.
Oh yes, of course.
What is the minimum? What is the minimum value of ISSC when we have to conduct multi-level?
Yeah, this is a good question. Scholars' opinion is divided, as traditionally is the case. Andrew Gelman in his book thinks that you can apply multi-level model always, regardless of how many second-level units you have, and regardless of how low ICC is. It wouldn't hurt you would still get a meaningful result. But I guess the majority opinion, or the dominant, the fashionable opinion believes that if ICC is less than 5%, it makes no sense to conduct multi-level model.
Thank you.
Well, recently I have seen a video on YouTube about multi-level modeling.
Right.
And the lecturer, actually he was saying that following up the question of how big ICC should be, that sometimes it is not important how large the value of ICC, because sometimes you are interested not in between country variance, but you are interested in the dependence between your dependent and independent variables in different countries. So ICC may be pretty small, but regression lines
May be different,
Yes.
different enough.
Mm-hmm.
Yes. Yeah, that's a good point too. Okay, let's move on to the next slide. So maybe you want to escape and move on to the script, because this is another model already. So we are going from the empty model to the fixed slopes and random intercepts model. So press escape and go to R. Let's do the empty model. I'm afraid you can't see very well. Can you see? Can you see the script? Okay, but anyway, let's. I don't know how to do it in RStudio, but maybe people sit close enough and they can see. It's alright. So let's simply execute the first couple commands. Library mass. It begins with library mass. Then there is a package, there is a data file called NL schools, which is an example from Sneeders and Busker, who use this data as a running example in their book, which perhaps some of you have read, and we are going to use this as a running example also, but in R. So this is a study of more than 2,000 8th grade students aged about 11 in 132 classes in 131 schools in the Netherlands, and only and now I can see what I'm reading, and hello. Okay, so we have the following variables. Lang is the language test scores. IQ verbal is verbal IQ. Class is class ID. GS class is GS, I think, class size. Number of 8th grade pupils recorded in the class. There may be others, not only 8th grade pupils. SES is socioeconomic status of pupils' family. COM, were the pupils taught in a multi-grade class, 0 or 1. And this means that some classes contain pupils from grades 7 and 8. Such classes are coded 1 on this variable COM. But only 8th graders were tested and are on the file, so 7th graders are not on the file here. And then we do some transformations. They are not that important. They're simply preparatory work. Among other things, it doesn't find. Did you do attach? Okay, and then yes. Let's execute the commands. Yeah. No. And go on. Execute them all one by one.
Okay.
One by one, that would be safer, because otherwise you can skip something. Okay. Yeah, go on. So we create a new variable IQ average. This is a class level variable representing class means on IQ. Go on. The script will be shared so you can execute it yourself if you want. So we're detaching, yes. Now we are going to center variables. We create an index. Now we use the function scale, which scales or centers, depending on the additional argument. Scale equals false. Oftentimes we want to center our variables because the coefficients will be easier to interpret this way. I'll discuss this later. Then, okay. Most importantly, we need the library LME4, which is a library for multi-level models. And now we are doing the empty model. So let's do the empty model. Okay. Can we look at the output more? Maybe you want to развернуть окно, нижнее окно, чтобы мы все на одном окне увидели. Okay, so this is the minimal output that we get, but it contains pretty much the most critical information. Yeah, it probably makes sense to show the screen rather than my belly.
We forgot about changing the direction.
Okay.
You can continue.
So let's see what it says. So it's a linear mixed model fit by restricted maximum likelihood. This is what it says. The formula language depends on one by class. So what does it say? So there is no explanatory variable, just intercept. And intercept is allowed to vary by class. So this is the minimal empty model. So this is technical parameter that we are not much interested in. And then the random effects. Now, let's recall from the presentation what are the random effects in the empty model. What are the random effects? Oh, this is not this. The previous one. Yes, this is the empty model. So what are the random effects here?
Country level residual variance.
Yes, there is eta j and there is epsilon ij. These are the two random effects. So we have to realize though that there are 132 etas and more than 2000 epsilons, right? But these are two random effects. And there is one fixed effect, which is gamma. Gamma is the fixed effect. Eta and epsilon are the random effects. So let's go back to the output R. So random effects. It starts with the random effects. So we have intercept that varies by class, and we have residual. Now we should, as I said, recall that there are many of these effects, 132 intercepts and more than 2000 epsilons. So we can retrieve them. If we are interested, we can retrieve all of them and show them on the screen or save them in an object. But here they give us standard deviation. Well, because this can be thought of as a random variable, right? There are 132 values for intercept. So intercept has a variance, and right, and there is a mean and variance. And because it has variance, it also has standard deviation. So here we have standard deviation, which is 4.4. And then there is residual variance, which is 8, right? Which is 8. So it gives us the number of observation and the number of groups, and there is fixed effect. And the fixed effect is what?
And mean?
This is the grand mean, the gamma 0 in my notation. The notation I used is closer to the notation used by Andrew Gellman in his book. Sometimes it will. It is also similar to Hermann Dülmer's, because Dülmer has taught in our laboratory several times. But it will vary from. It will be different from Dülmer's in a couple of aspects. So let's go back to the script and calculate the ICC. And we can simply use the figures provided by the program. It gives us the value of standard deviation for intercept and standard deviation for residuals. If we square them, we get variance. So we have alpha variance, and we divide it by the sum of alpha variance and epsilon variance, and thus we get ICC, which turns out to be about 1/4, 0.23. Alternatively, it says in the script, you can use a ready-made function. There is a package called ICC. Oops, where is it? There is a package called ICC, and there is a function ICC estimate, and you do, and the syntax is as follows: class, language, data, and it will give you not only the value of ICC, but it will also give you a confidence interval for ICC, which perhaps may be good. So this is the empty model. Is everything clear so far?
Yes.
Yes. Then we can move to the next model, which is fixed slopes and random intercepts. And let's look at the presentation first. So can we go back to the presentation? Yes. So fixed slopes and random intercepts. This is the model that I used on the first slide as an example of multi-level models. So what we have is an intercept that varies, alpha j, but b is fixed. It does not vary, so b remains fixed. So we assume in this model that all slopes are the same. That is, each country, or each class for that matter, has its slope. Right? So the only difference between the classes is the mean grade. So some classes are good, some classes are bad, but the relationship between IQ and the grade is the same in all classes. This is what it says. Now alpha is moderate as it was previously, gamma a constant, and unexplained variance on country level, and the mixed equation looks as follows. So there are there are two random effects and there are two fixed effects. So the two fixed effects now are gamma 0 and beta, and the random effects are the same as before: unexplained variance on the country level and unexplained level variance on the individual level within countries. Now you have to remember that epsilon is within countries. So compared to the empty model, this model would reduce epsilon variance, but would not necessarily reduce alpha variance much. Sometimes it can actually reduce alpha variance, because when you introduce x if mean of x varies by country, right? If it correlates with the country or with the class, if there are, if mean IQ is greater in some classes than in other classes, right? Then it would also reduce alpha variance because of that. Do you understand this? Okay. But generally, otherwise, the variables, the explanatory variables of the first level will not necessarily reduce alpha variance. But this model is supposed to reduce epsilon variance. This is a must. If it doesn't, that would be very strange. So, and notice also that in this particular case, alpha variance is identical to eta variance, as was also in the case of empty model, because alpha is modeled as a constant plus epsilon. So the variance of alpha is the same as the variance of epsilon, because the constant has no variance, right? But this will not necessarily be the case in other models, but in this model this is the case. Alpha and epsilon variance are equal. So let's look at the script now. And let's execute the fixed slopes and random intercepts models. This is how it is this is what the syntax looks like. We have IQ, the country level intercept that varies by, the class level intercept that levels by class. So it starts with random effects again, and the random effects are the same as before, epsilon and alpha. So the first is alpha. So there is variance and standard deviation, and there is residual variance, epsilon variance. There is also variance and standard deviation. The output looks different now because it is summary of model M1 rather than simply M1. If we typed only M1, we would get a less copious output. So then there are fixed effects, and there are two fixed effects: the intercept, which is gamma 0, and there is IQ, that is beta. And both are very significant. So so far so good. The correlation of fixed effects is very small. Well, normally intercepts and slopes have a negative correlation, but not in this model. This comes because consider a regression line. It has a certain intercept and a certain slope. Then if you remain at the center of the same space and draw another regression line, it has a larger slope but a smaller intercept, right? So therefore intercepts and slopes generally correlate negatively. So what else can we say about this model? Maybe it's a good idea to compare the standard deviations of alphas and epsilons in this model with that of the previous model. So now it is 3 and 6.5, and it used to be what? Can you scroll up?
4.
It was 4 and 8. So as you can see, both alpha variance and epsilon variance was reduced, and this is because we introduced x. So we would have expected that epsilon variance must be reduced, But the fact that alpha variance was also reduced suggests that there may be a correlation between mean IQ and the class. Okay, I guess now we can move on to the slide. Next slide, yes. And this is fixed slope random intercepts with a second level predictor. So this model is similar to the previous model, but we add a new variable z on the second level. So on the first level, the model is the same, right? There is alpha j plus beta, which is fixed, times xj plus epsilon, right? But look at how alpha is modeled now. We try to explain alpha here. So rather than just saying there is a gamma and unexplained variance epsilon, we introduce gamma zj, right? Z is a second level predictor. It varies by j, not by I, right? So here we expect that epsilon variance will be further reduced, and alpha variance here is no longer the same as eta variance. Eta variance is now smaller than alpha variance. Do you see this? Alpha variance must be larger than eta variance. Eta variance is smaller than alpha variance because there is an explained part and an unexplained part in the alpha variance. Okay? So gamma z is the explained part and eta is the unexplained part. And the mixed equation now looks a little bit more complex, and it could be rewritten as in the bottom of this slide in order to separate the fixed part and the random part. So in the random part we have the same two terms, epsilon and eta, but we expect that eta will be smaller now. And there will be three fixed effects. So there are two random effects and three fixed effects, gamma, 0, gamma, and beta. Here. So let's go back to the script and execute random FSRRI M2, and let's look at the summary. Yeah. So this is what we have, IQ plus COM. So they are not distinguished, but IQ is the first level variable and COM is the second level variable. And program recognizes this, even though for us it's
What is it like?
COM.
Yes.
COM is stands for combination. It takes the value of 1. If there were 7 graders in this 8th grade class, and the idea is that when the class is mixed, when there are some younger and perhaps dumber kids in the class, the general level of the class goes down a little bit because the teacher has a harder job. He has to dumb his class down for younger kids a little bit, I guess. So there is IQ and COM, and the intercept varies by class. And let's look at the random effects. So the random effects are actually the same as class, and it is less than 3 now. So this is alpha variance, or rather epsilon variance, I'm sorry. This is epsilon variance, it got reduced. I mean, not epsilon, eta. 2.944 is eta variance. It's got reduced compared to the previous model, and the epsilon variance remains actually at about the same level
Yes.
as it was, so it is not reduced very much. But there is a slight, maybe a very small and insignificant decrease. Now let's look at the fixed effects. So we have the intercept, which is gamma 0. We have beta, which is also fixed and is significant as it was before. And there is the effect of COM, which turns out to be also significant. What it means, so 1 is the combination class, and people in the combined class get on average lower grades than those people who studied in a regular class. And now there is a correlation of fixed effects and just additional information. So, can we move on? Are we good? Okay, then let's move on. So the next model that we take is the random intercepts and random slopes. So on the first level again, the model looks exactly the same, alpha, beta, x, and epsilon. On the second level, we model alpha as we did before, a couple slides before. So there is no explanatory variable, but the difference here is that we model beta. So beta now is a variable, it is not a constant. It is not a constant, so the slopes are allowed to be different. We don't pretend that we know why they are different, because there is no explanatory variable on the second level, but we say that they are different. So the mixed model looks like this, the fourth line, and it could be rewritten, separating the fixed part and the random part. So let's examine this, because this is interesting theoretically. There are three random effects now. So the eta variance and the epsilon variance are familiar. But what is it, this eta times x? What does it do? This term actually models heteroskedasticity, because error obviously depends on the level of x, right? Eta 1 is an error term, and it is multiplied by x, so it must mean that, there is a relationship. So graphically it could be thought of as follows. So in this model, so previously the slopes were fixed for all classes, right? But now we allow them to vary. So there may be a slope like this here, and a slope like this here. This being IQ, and this is being the grade for the language class, right? So if you look at this, there is obviously heteroskedasticity, because think of this, individuals who are placed along this line, and then individuals who are placed along this line, and there may be some lines here also, right? So the variance here is relatively small, variance here is relatively large. This is heteroskedasticity. Heteroskedasticity is not a problem in multi-level models, because it is modeled, it is a part of the model, so it is not a problem, unlike in classic regression. You only have half an hour, so maybe you want to bring your battery.
Давай.
Да, у меня вот, кстати, даже кружка есть. Я просто водички перелил. Спасибо. У меня кончилась. So this is generally a part of the varying betas, right? So eta is the unexplained variance of betas. Eta 1, I mean, the one that is multiplied by x. Eta 1 is the unexplained variance of betas. And we don't have the explained variance of betas here because we don't have z, the class level, the second level explanatory variable, right? So other questions? Are you good? Okay, then let's move on and do the R script again. So there must be okay, random intercepts and random slopes. This is how it's done. Oops, yeah, this is how it's done. You see IQ and IQ by class. So there is no one because IQ is the second order variable, the first order variable, whereas intercept is the zero order variable. So when we add IQ, the intercept is assumed, so we don't have to write it, okay? It's just like in the hierarchical of linear models. So IQ by itself and then IQ varying by class. So let's examine the output. Right. So what we have here is again 3 random effects now, not 2. So the top one is the epsilon 0 variance, right? Then goes the epsilon 1 variance, the one that is multiplied by x in the equation. And finally there is epsilon variance, right? And there are 2 fixed effects, gamma 0 and beta 0. What is it called in the presentation? I don't recall what is it called in the presentation. Gamma 1, gamma 0 and gamma 1. So the fixed effects are gamma 0 and gamma 1. And can we move on? No questions?
And what is that correlation? Minus 0.7.
That's correlation between IQ, that is epsilon 1, and epsilon 0.
Between slope and intercept.
Between the unexplained variance of intercepts, eta 0, and unexplained variance of slopes, epsilon 1. And it should be negative, because slopes and, I explained that slopes and intercepts typically correlate negatively. Okay.
Now, one more question. Here we have a correlation about 0.37.
Oh, that's correlation of fixed effects. I thought you were talking about that correlation, minus 7.9.
That's again. So
But this is correlation of fixed effects. So this is correlation of gamma 1 and gamma 0.
But if this correlation is rather high, for instance 0.8 or 7, could that be a problem?
I don't know. I don't think so. Generally, I perceive this as some technical information that is not of much interest. Okay, let's go back to the slides, and this is the final slide because this is the most complex model. A model with a cross-level interaction effect. So again, on the first level, the equation looks similar, alpha j and beta j. So both are variables now. So there are random slopes and random intercepts. now we model both alphas and betas using Z, which varies by J. That is, this is a class level variable. So we explain part of the alpha variation and part of the beta variation. But then there remains some unexplained part, eta 0 and eta 1. I noticed that I keep confusing letters eta and epsilon. So when you asked me about the negative correlation, I used, I think, epsilon, but I should have said eta 0 and eta 1. Eta 0 and eta 1. Then we can write a mixed equation, the fourth line, simply by putting alphas and betas into the equation. And the mixed equation can also be written as follows. So we have now three random terms, eta 0, eta 1, and epsilon, as before. But we have now more fixed effects. We have gamma 0, 0, we have gamma 0, 1, we have gamma 1, 0, and we have gamma 1, 1. Now let's explain what all those fixed effects mean. So, what is gamma 1, 1? Let's begin with this. What is gamma 1, 1?
Well, let us say this is the part which is explained in slope variance
Exactly.
by zeta.
Yes, so this is explained heteroskedasticity, or this is the explained variance of slopes. This is exactly right. This is exactly right. What is gamma 1, 0?
I think this is the ridge slope.
This is, yeah, the grand slope, or the mean slope. You can think of the mean slope. Yeah. What is gamma 0, 1?
That is explained variance in intercepts.
Yes, this is
I see.
correct. This is the explained variance of intercepts. Gamma 0, 0 is
Mean.
of the intercept.
grand intercept. It's no longer the mean. You can think of it as a mean, but when we add variables, you know that the intercept cease to be means, because the intercept is the value of y when all variables are 0, right? When all other variables are 0. So it's not necessarily the mean, but you can think of it as a mean. Sometimes it is convenient to think of it as a mean. Okay, so good. Now eta 0 is
Unexplained variance of slopes,
of
intercepts.
intercepts, yes. Eta 1,
That is the same for slopes.
unexplained variance of slopes, and epsilon is clearly residual individual variance within countries. I mean within classes. So why is it called a cross-level interaction effect?
Of course, we have a multiplication of z and x.
Yeah, we have z and x. It's not transparent if we write out the first three lines. It's not clear where the interaction effect is, but if we write the mixed equation, then it is clear that z must be multiplied by x, and this is the cross-level interaction effect. So the cross-level interaction effect tries to explain the variance of slopes with z. So again, we can sort of write it to make a picture. Alright, so there is the first level, and there are many lines and they all have different slopes and intercepts. Right? Why do I write it like this? Because I assume this is IQ, right? So these are apparently a good school, and this is apparently a very bad school. And what's the difference between good schools and bad schools? The basic difference between good schools and bad schools are dumb kids. When kids are dumb, there is a great difference in terms of why, right? But when kids are smart, there is still some difference, but the difference is not that big. So good schools are good for dumb kids. Then we try to explain the intercepts in different slopes by another variable, z. So there are two more graphs here essentially. And so you see that z is not a continuous variable. In our case it is a discrete variable, but can be also continuous. Like IQ average of a class. That would be a continuous variable. But nevertheless, so there are only two meanings, two values, 0 and 1. And let these be alphas and these be betas. So this is the second level, right? Whereas this is kind of the first level. So the slope for the combination classes is must be bigger, right? And the intercept for combination classes must be lower. So yes, so it looks sort of like this and sort of like this, and therefore they correlate negatively.
So once again, so the first line stands for the intercept and the second for the slope.
No.
These are intercepts, these are slopes. But in fact there is nothing in between. It's just a gimmick to help you understand what's going on, because what we have in fact is a distribution of alphas here and another distribution of alphas here, but this is the mean and this is the mean, and we sort of can connect them like this, although this doesn't have much sense. Sometimes it's helpful. And likewise here, there are betas here and there are betas here, so there is a mean here and a mean here, and we can connect them if we want. So this is the cross-level interaction effect. Let's do it in R. And see the output. It's summary M3, but we need summary of M4. Is it, yeah, it has the interaction effect. You can see that this is the cross-level interaction effect, IQ times COM. COM1 means that this is the dummy variable for combined classes. It could be otherwise, that would become 0. Okay, so what we have here is 1, 2, 3 random effects and 1, 2, 3, 4 fixed effects. Right? And we have already kind of discussed what each of them means, but let's do it again here. So random effects class intercept, this is what? What is this?
Unexplained variance
Yes,
of intercept.
exactly. So this is eta 0.
Mm-hmm.
This is eta 0. And its variance is reduced. It is less than 3. It is now even less than 2.9. So we have been improving the model because we now explain the variance of intercepts to a greater extent than we did in other models. Okay, then random effects IQ. What is it? Random effects IQ.
This is unexplained variance of slopes.
This is correct. So this is eta 1. That is, eta 1. Residual is clearly the epsilon, or the unexplained residual individual variance within countries. Okay. Now we get to the fixed effects. So the intercept here is, it's gamma 0, 0. IQ is, what is it? Gamma, I think gamma, gamma 1, 0, right?
Slope.
Yes.
And
Yes.
com 1,
Gamma 0, 1.
0, 1.
The direction that is
Gamma 1, 1.
yes.
Okay. So this is a short introduction. We can go on unless you're tired.
Can I quickly
yes.
ask just as for random effects, so the intercept is then here stands for the intercept, right? Ground intercept.
In random effects,
In random
no, in random effects this is not grand intercept. In random effects this is eta 0.
Mm-hmm.
This is the variance of intercepts, because see, there is no single coefficient. There are in fact 133 coefficients. They are not given all. We can get them if we want, but it gives us the variance and standard deviation of this vector. There is a vector of 133 values that are added to the grand intercept. And this is the unexplained part of the variance of intercepts.
And IQ stands on what?
In the random effects,
In the random, yes.
IQ in the random effects stands for eta 1, which is the unexplained variance of slopes. Because there is also, you can look at the equation. So look at the,
Yeah.
at the last line is nice to look at because it groups the random effects and fixed effect. So we have 3 random effects. So eta 1, eta 0, eta 1, and epsilon. So these are the 3. Yes, there are many of them. 133 eta 0s, 133 eta 1s, and more than 2,000 epsilons. So these are vectors of values, and we can calculate variance and standard deviation for each of these vectors. We can also, if we are interested, retrieve all of them. We can retrieve 133 eta 0s as many eta 1s and more than 2000 epsilons. But the grand intercept here is gamma 0, 0. This is the grand intercept. Now, gamma 0, 1 is COM in the fixed effects. Gamma 1, 0 is the IQ in the fixed effects. And gamma 1, 1 is the interaction of COM and IQ in the R output. Okay. So we started at 3, right? So about an hour. I can go on with the next part if you're ready. I don't know.
Maybe I think that maybe we can interpret interaction effects.
Yeah. Maybe.
Sometimes it's really difficult.
Oh, you want to interpret the interaction
yeah.
effect?
We can compare the moves.
Okay. So there is so fixed effects only. We won't go into 133, right? But fixed effects. So this is not too difficult because COM is a binomial variable. It is a dummy. So let us we have gamma 0, 0 plus gamma 0, 1 times z, or COM, plus gamma 1, 0 times x, or IQ, and plus gamma 1, 1 times zj xi. Right, and now we can put in numbers, but I will round them to make it easier to interpret. So let's say 42 plus let's say 2 times z minus 2 minus 2 times x and plus 0.5 times zj x. Actually, I can do 2.5 here as well. Alright, so now let's write out partial equations. Alright, so there are basically two situations. The first situation is zj equals 0. So these are uncombined classes. Right? So this turns into 0 and this turns into 0. So what we have is 42 minus 2. Is this right? No, IQ has a positive sign.
Yeah, it should be different. Minus 2.5 and plus 2.
Now it's correct,
Okay.
right? And then there is this other situation when we have z equals 1. So if z equals 1, this is this turns into 2.5, so this becomes like 39.5. So this is 1, so this becomes 1/2 x. So it becomes plus 2.5x. Right? So, just as I told you, what you have, alpha and beta, as predicted by z, right? So takes only two values, right? So alpha for here, the mean, because there are 133, but this can be thought of as mean, right? So here the mean is 42, and here it is 39, whereas here this is 2 and this is 2.5, but these are means, there are many more, right? And if we want to go to the first level, so this is x and this is y. So what we have is okay, so 39 and 2.5 will look some, I exaggerate, but it will look something like this, and 42 and 2 will look something like this. All right? Just as I told you. Come, but these are Netherlands. The Netherlands is a very prosperous and advanced country. But you could think of it as a St. Petersburg, and instead of Z being Com, think of Z being the working class neighborhood. And then you have this situation. So students in working class schools, if they are dumb, they do poorly, much poorer than dumb kids in good schools. But if they are smart, they do almost as good as kids in good schools. So this is the meaning of the cross-level interaction effect.
And here we have a coefficient for IQ for classes where comb is equal to 0. Am I right? I mean that coefficient. That.
I'm not sure which one.
The coefficient of IQ.
It's 2.337.
So that is for schools where comb is equal to 0. I mean IQ coefficient here.
The IQ coefficient here is 2.5. Well, it's 2.337, right? But I wrote is 2.5. This is I rounded it up, right?
Yeah.
But then there is an interaction effect of also about 0.5, and so it adds to poor schools, to combined schools. Therefore, the slope is greater.
Yeah. I mean that value. That is when x comma is equal to 0.
Oh, t value.
Yeah.
You're
Yeah.
referring to the t
Yeah.
value. Yeah, the t value it gives us for the value of com equal 1. But if you're interested to find out about the t value for in com equals 0, you have to change the base category. It's possible. And then you can calculate other conditional effects, right? Because, for instance, this effect might be significant or insignificant. But right now we know that it is significant. But if it was the other way around, and this would be potentially, this would be greater and the other would be smaller, and we were not sure about the smaller one. If it was significant, then we would have to change the base category to calculate conditional effects, yes.
Have you covered the issue about how to choose the model?
No,
Not yet.
not yet. I only introduced the basic models. This is the next topic, how to choose a model.
Okay, so I'm in time.
Okay, do you want a break or shall we continue? Huh?
We need a break.
Very
Short
good.
break.
A short break, yes. Yeah,
Сколько будет время?
difficult. So I want to concentrate on model selection and on visualization of the model. And if we have done, then we have next time on Tuesday enough time to cover logistic regression. But if we don't, then visualization will be we'll cover visualization next time. So there are certain principles of testing the effects in multi-level models. First of all, these multi-level models are not OLS regressions, right? They are maximum likelihood regressions. So what you do is a chi-square test, just as we did with log linear models. You remember this. ANOVA, model 1, model 2, and it'll compare. It runs an incremental chi-square test that helps you decide whether you should choose simple model or a more complex model. But in multi-level model there is an additional problem. You have to test random effects and fixed effects, I'm tired already, separately. You cannot test them simultaneously. So let's do this script. So we have 4 models right here. So this is the same database. So there is an empty model, then there is a, oh, actually tell me, what is model 1? What is model 1? What kind of model is M1?
And ANOVA?
No, M0 is ANOVA. M0
Yes.
is the empty model. What is M1?
Looks like multiple regression.
Fixed slopes, random intercepts.
Say again, please.
Fixed slopes, random intercepts.
Very good. Fixed slopes and random intercepts. What is M2?
With second level predictor, the same.
The-
Fixed slopes, random intercepts.
With second level predictor. Very good. M3,
Random slopes, random intercepts.
random slopes, random intercepts. And M4,
The same
The
regression.
same rejections.
M4 is the cross-level interaction effect. So models have to be nested, but this is always the case. Even in OLS, you test nested models, right? Random effects have to be the same in both models. If you want to test fixed effects, then make sure that in both models, random effects are the same. So if you have 3 random effects in one model, then the same 3 random effects must be in the other model, and then you vary fixed effects to check whether you need one particular fixed effects or not. Okay. And both models need to be fitted using full maximum likelihood, because by default, at least in LME4, the program does restricted maximum likelihood. But in this case, you want to run full maximum likelihood, because otherwise the chi-square will not be correctly reported, right? Because restricted maximum likelihood makes it easier to calculate effects of the coefficients, but in terms of deviance, it calculates it differently. So restricted maximum likelihood is all right when you do like preliminary work, but when you do prepare to test particular effects, you want full maximum likelihood. Yeah, that's even in Stata it would be the same. I don't know how to do it in Stata, but even in Stata you should do this. And perhaps I'm sure there is a way in Stata to do
And
this.
what do we do if we get different results with state and tar? Because state and tar yield slightly different results sometimes, and if we use some more sophisticated technique like body set analysis, I get completely different results.
Like which analysis?
Body set analysis. I use same variables, same data set, same transformations, and state and tar give me completely different solutions. What should be done in this case when two softwares give you different solutions with the same data sets and variables?
Normally this should not be the case. So sometimes iterative models are based on starting values, and it may depend on the seed. You know what I mean? The
Seed.
there is a random generator,
Okay.
random number generator in both Theta and R, and they might start with different starting values. So this is my first idea. Maybe even though you have checked, I heard you what you said. Maybe your models were slightly different, had somewhat different specification.
They were absolutely the same actually.
Maybe the method,
But the developers of the packages are different,
right?
and the modeling is very new. But even with logistic regression, I get slightly different coefficients with theta and tar and p-values. There's always a slight difference between the two softwares. It happens. I just wanted to ask.
Yeah, I didn't do a systematic comparison, so I cannot answer this question satisfactorily. However, I know that some other people have done systematic comparisons of software performance for different types of models. So I know, for instance, a work that was done on multi-level modeling, comparing different packages in R and Stata and HLM and what have you. And generally, you know, the updated R packages perform very well compared to other software. If we are to believe this article that was published in a prestigious statistics journal of statistics, but I don't know. I can't say it for all models. But I know that the R is updated constantly. So
Yes, and state is not.
yes, and if you look at the packages, so the last packages, you know, up like August 2015, right? Whereas in Stata, I think they do not update their software as frequently as they do.
This
in
is
R.
true. But Stata has certain commands that R doesn't have. So sometimes Stata is also used. Okay, thanks for this.
But I don't have a definite answer, just some ideas. All right, so we do M3 and M4 modified. Notice ML, so that they are different from M3 and M4 because they are run with full maximum likelihood. To do it, you need this additional argument, restricted maximum likelihood is false. And notice also, let's check whether we are going to test fixed effects, right? So fixed effects must be different, but random effects must be the same, right, in these two models. So let's decide what's the difference in terms of fixed effects. So what's the difference between M3 and M4 in terms of fixed effects?
We have two more fixed effects in model 4.
Right, which are those?
there is the influence of COM and interaction term.
Yes, so there will be two more fixed effects in M4 compared to M3. What about the random effects?
Yeah, this in
Yeah, so there will be unexplained eta 0, eta 1, and epsilon. So there will be three random effects, but these random effects are the same. So therefore these two models will be comparable. And now we can run them and do the ANOVA. Control R.
Да.
So this is a standard more or less output for all chi-square testing. So we have two models, and the models are specified for us so that we don't forget them. And then there is residual, there is degrees of freedom, 6 and 8. So spent for the regression. And so M4 uses two more.
Oops, sorry.
Yeah, M4 uses two more degrees of freedom because, as Anna correctly said, that there is one coefficient for COM and one extra coefficient for the interaction term, the cross-level interaction effect. Right? So then there is AIC and BIC, and you already know what this is from my lecture on log linear modeling. Right? So there's AIC information criterion and Bayesian information criterion. So both of them are adjusted chi-square coefficients essentially, where AIC punishes it for lack of parsimony. Bayesian punishes it both for lack of parsimony and also sample size. Then there is log likelihood coefficient and deviance. Deviance is our chi-square. The difference between deviance is also chi-square. So 30 minus 14 is 16, right? So this is the chi-square against 2 degrees of freedom. So 16 points in chi-square against 2 degrees of freedom is a large coefficient, therefore it is significant. And the rule is very simple, as I told you. When the coefficient is large, you choose a large model. When the coefficient is small and insignificant, you choose a small model, right? So in this case, the reduction in deviance is significant for 2 degrees of freedom. This means that these 2 degrees of freedom were well spent. It was a good deal, and therefore we should keep the large model. So model 4 is better in terms of deviance against chi-square against degrees of freedom compared to model M3.
You mean coefficient, which is 16.744 is big.
This is chi-square, yes. This is chi-square, and this is the difference of deviance between these two models, M3 and M4. Look at the deviance. It's 15 to 30 and 15 to 14, right? So the difference is 16. And the degrees of freedom that were spent were 6 in model 3 and 8 in model 4. Why 8? Because there are two more coefficients in model 4 compared to model 3, right? So
Can we judge on the basis of these two parameters as AIC big?
I don't know how to do it, quite frankly. The difference will be, automatically. I know how to do it manually because it's easy in R. So the difference in terms of AIC is 12, and the difference in terms of big is 2. Right?
Significant difference.
Right. So big, as I told you, it punishes you for lack of parsimony. So each extra coefficient, as Ikaki also does it, but big also punishes you for large sample size. So if we're going to judge by big, then we have 2 points of chi-square for 2 degrees of freedom, and this is a bad deal because this is small. Even for 1 degree of freedom, you want about 4 points of chi-square. For 2 degrees of freedom, you want 7 or about 8 points of chi-square, right? So this is not enough. On the other hand, if you judge by Ikaki information criterion, it is 12. So it is also significant. 12 against 2 degrees of freedom is significant. The choice is for the researcher. But it says that the difference, Big says that the difference is not that great. On the other hand, the rule with Big is very simple. It's not like you take the difference of 2 bigs. The rule for Big is different. You simply choose the model that has lower Big. So you do not really do this. You do not calculate the difference. So the lower the Big, then the better the model. So even this is only 2 points.
And the same applies with AIC, so you need to
Yes.
choose the lower,
The lower.
comparing to the null
Yeah.
setting,
Well, in our case, the null model is M3.
M3.
In this particular case, because we compare M3 against M4. M4 is the more complex model, so M3 is the null model for us here.
But if I can go in different directions, because
Yeah.
sometimes
They do. I showed you, or did I? No,
I don't
I didn't.
remember, but
Oh, that was the
I-
big sample, the big example that I didn't show. But yes, sometimes IE and Big go in different directions, and they produce different best models. And my trust is more for Big, but this is from my personal experience. But that example that I wanted to show you, but didn't have enough time, there was a very large sample, like 30,000 cases. And if you used AIC, then you would have some very strange coefficients, like father status and the sex of children. Which would mean that in wealthier families, parents select the sex of their child, which could not be the case in America because these are data for Americans who were born about 100 years ago, like in 1915, right? So they didn't practice selective infanticide at that time point, not in America anyway. So clearly the program, there was a small difference in frequencies, and the program decided that it was a significant coefficient, but it made no sense, right? It makes no sense at all. But when you use Big, this coefficient gets deleted. So unfortunately I didn't have enough time to show you that example, but it's a good example. Okay, shall we move on? So let's get back to script, and we now do the same. We want to test random effects, and the logic is exactly the same. Models have to be nested. Now fixed effects have to be the same in both models, and both models need to be fitted using full maximum likelihood. So we can do it quickly because you now understand the logic and could be a little quicker, right? So let's simply do it.
Yes, M1 and M3.
Okay. All right. So M1 has IQ as fixed effect, and intercept as random effect, and of course there is also epsilon, right? And M3 has IQ as the fixed effect. Now it has random slopes, so the random effects are different, but the fixed effects are the same in both models. So we compare these two models. The chi-square difference is 22 points for 2 degrees of freedom. This is very significant, and so we choose the larger model, which is in this case model M3. So we know that we have to keep all random effects that are in model 3. Okay, so this is it. Okay, this is 5 o'clock already, so we didn't do visualization. We'll have to do visualization next time, and hopefully we'll have enough time for logistic multi-level. Okay, this is it. Have a good weekend, those of you who do